Hi, welcome to this plenary session. I'd like to introduce Moon Duchin. Her research focuses on discrete geometry and randomized models with application to the study of voting and democracy. She's a professor of public policy and mathematics at Cornell University. A prominent voice on fair redistricting, Duchin has developed mathematical models to analyze the potential and actual outcomes of changes to policy and voting. Sorry, not to ruin that. She has served as an expert on redistricting litigation and advised commissions and government bodies in numerous states. Recently, her work has turned to the study of alternative systems of election, such as ranked choice voting. Duchin's research was recognized with an NSF Career Award, a Guggenheim Fellowship, and a Radcliffe Fellowship, and we're happy to have her here today.
I saw the slide starting to advance and got worried. All right. Okay, great. Hi, folks. So here's my attempt for this talk is going to be to tell you a few different stories that kind of bring things together. So for starters, I called the talk The Data and Science of Elections, and I want to tell you both about the data and about some of the science/mathematics that goes into working with it. I want to actually really drill down a bit on the application domain and talk about elections. And today is Tuesday, 2 weeks from one of those coming up in which this particular state that we're in today will be extremely important. So if you, like me, are driven to distraction by all the uncertainties of this election, maybe I'll give you some information over the course of this talk that will at least distract you positively. Okay, so for starters, I asked DALL-E to draw me mathematics of data science and then democratic mechanisms. And what I'm going to do over the course of this talk is try to give you ways that the mathematics of data science contributes to our thinking about democratic mechanisms, but also some of the ways that this application domain gives back. And if you take a close look at these images, there's all kinds of great, OpenAI artifacts, like learning spelled interestingly, and a real fashion show happening on the democracy side. So this is my new favorite sport. Okay. All right, so I'm going to start with the longest one of the 4 stories that I want to tell you, which is to talk a little bit about how I got interested in all this, which is work on redistricting. So in particular, I'm going to tell you about some ideas for using Markov chains to help us understand redistricting, and in some cases to help improve the way we do it. Okay, so what is redistricting? For the purposes of this talk, I mean political redistricting, although there are many, many kinds of ways that we have to divide up territory. So for me, redistricting is dividing territory into connected pieces, which we're going to call districts, and we're going to use those pieces for conducting elections. Just the term redistricting doesn't carry with it any assumptions about what kinds of elections are going to be conducted on those districts, right? It's just the partition problem that kind of lives upstream from however you then conduct the election. Okay, so sometimes when we think about redistricting, we kind of imagine it as a freehand problem where you're actually drawing shapes and you get all the kind of continuous freedom to draw any kind of crazy shape that you want. But one thing that I'm going to try to convince you, especially when we actually take a look at how the data comes to us, is that this is actually a fundamentally discrete problem. We're going to take a finite number of units, a large but finite number of units, and we're going to assign them in a contiguous manner, as we'll see. Okay, and so in particular, I want to use the formalism of graphs and model this as a graph partition problem. And we're going to borrow ideas, in particular from statistical physics, Markov chains, and kind of dynamical reassignment to help us think about how that universe of possible configurations is actually structured. Okay, so now let's actually take a little detour for a few minutes and actually look at the data and some of the mess that comes with trying to do this for real. Usually, so this is backwards, right? Usually when you see a talk that's giving you, applied modeling, as I'm about to do, you hear about the math first, especially at a venue like this, and then maybe there might not be that much attention to the data. But it's gloriously disgusting, and let's take a little detour and take a look at that. Okay, first, if you want to build the data set, there's one non-disgusting place to go shopping, and that's the Census Bureau. So the Census Bureau releases the cleanest and nicest data that you can hope to use for problems like this. In particular, they have a hierarchy of geographic units. And so here's a network of the counties in what state? Missouri, yes. And then within that, the Bureau divides them into nested pieces called county subunits. Those aren't used for very much. Instead, they're also divided alternatively into things called census tracts, which were originally created for the purposes of public health statistics in order to give us longitudinal information about public health from one census to the next. Tracts are subdivided into things called block groups, which are smaller and they nest inside, and those are subdivided into things called blocks. So census blocks are the finest unit in this whole geographic hierarchy that's given to us by the Bureau. Typically, a block might have no people or up to a few hundred people. It surprises folks sometimes to hear that blocks can have no people, but it was the case, for instance, in 2010, that 40% of the census blocks in the country had no people, right? And part of that is because the Bureau is trying to balance a couple things when it draws these geographies. One is total coverage, another is trying to make the sizes not too different, as in populations, and another thing is trying to make the sizes not too different, as in areas, right? And so when you're trying to balance all those things, it produces really kind of heterogeneous data. Okay, so Missouri in particular had some almost 350,000 of these census blocks that you're seeing in that bottom picture in 2010. Okay, and then what I'm showing you in these pictures is what we might call a dual graph based on the adjacency of those units. So these pictures have a node for each unit at the level indicated, and then an edge between two units if they share a boundary of positive length. Okay, so I'm not putting down edges for corner adjacency, but that's just a choice. I could if I wanted. Great, so this is the good news of building the data set. But the bad news is if you want to study elections, these units won't do. And that's because elections are administered by states and even localities, and the votes are counted and reported on geography called precincts. And the federal government does not control the drawing of precincts. It's the states, even the counties, sometimes even the towns that change the boundaries of precincts. But you have to know where they are if you want to do this kind of work. So a summer program that I ran together with Justin Solomon of MIT in 2018 and 19, in 2018, we called all the counties in Ohio and asked them the question, where are your precincts? 46 of the 88 counties gave us shapefiles, which are kind of the go-to format for geospatial data. It's usually used in GIS. 27 counties sent us PDF maps. Beyond that, 8 counties sent us paper maps. And here's an actual one that we got in the mail. If you look at this, you'll notice magic marker and tape is involved in telling us where the precincts are on this map. And 7 had nothing at all that they could share with us. Okay, and then what we had to do with this is take all of this information. So this is actually a picture. We ended up making an art exhibit out of this. So this is actually a picture of those maps as they came to us. And then we had to try to take those and kind of fit them together into a picture of Ohio, right? And this is a really complicated kind of geometry problem, really, computational geometry problem, that I only have time to say the littlest bit about, but I want to give you a sense of all the work that goes into making the data. So here's another example that I found striking. Anybody know where that is? That's Boston. Or is that Boston? So these are 2 shapefiles that I was provided by the city of Boston when I was their expert witness in a court case. They had every incentive to give me the best data, but gave me these 2 from different timestamps, which just aren't quite the same. And the differences really, they have to do partly with whether the water is included, but there are other small differences that are hard to reconcile between the two. And this is actually pretty typical. Even a city like Boston, which has a pretty good data office and apparatus, is gonna have some glitches when it comes to maintaining data like this. Okay, so here I want to highlight the work of my collaborator, Jen Cleland, who's done some really beautiful computational geometry work to take a messy shapefile and turn it nice. So you can have various kinds of problems when shapefiles are messy, overlaps, gaps, and you have to be a little bit smart about how to fix them. And so one of the several open source software packages that's maintained by my lab is one that Jen has done a lot of work on in the last few years, which is called MOP, what geographers call the modifiable areal unit problem. And there's some really nice math in trying to get it right in a way that maintains intended adjacencies. So think about this as a problem where there's a true tiling, but you've been given a noisy version, and you're trying to recover the true tiling with its original adjacencies. So there's some really interesting math that goes into that. Okay, so that was the end of my aside on the data. And now that we've got the data and can take it for granted, let's do some math to it. All right, so I want to talk a little bit about this state space of partitions, this kind of universe of possible ways to do redistricting. So a very natural idea, if you want to think about understanding all the options, is to borrow from statistical physics. So this animation on top should be familiar to a lot of folks in this room. This is Glauber dynamics in what's called the Ising model of ferromagnetism. So you have a grid, and then every unit has a spin. In this case, plus or minus is yellow or blue. And then there's some dynamical system that's taking you through time steps and changing things. And in particular, the basic move in Glauber dynamics is to flip a single unit from one, in this case, color to another. Okay? And if you do that and pay attention to some kind of energy as you go, you can encourage configurations that are more clustered or less clustered and so on. Okay, so this seems like a natural thing to try to borrow, and on the bottom I'm going to try to do that to a districting plan. So now instead of just 2 spins, I have a bunch of districts, and I'm starting out with essentially vertical stripe districts, and then I'm going to run this dynamical system where I query a node at every time step, and I try to change its color. Okay, so you see this isn't working super well in the sense that it started out with vertical stripes, and as we know, one thing that we like our Markov chains to do is forget where they started. We'd like them to be able to explore and get lost, and this one's having trouble losing its memory of where it started. Does that make sense? Okay? And one reason, I mean, the key reason that that's happening is that districts have to be connected. They have to be contiguous. But most moves that you'll propose in this grid are going to break connectivity, right? And so they'll be rejected, and only very particular moves are going to be accepted, and it's just having a hard time making big changes in the configuration. Does this make sense? Okay. So this turns out to really be a meaningful obstruction to using this kind of dynamical system to understand the world of all the ways you can redistrict. So here's an example in, I like name that state, you'll have to forgive me. Anyone? Kentucky. And here what I've done is taken the block groups in Kentucky, started them out at time 0, and then walked them through 40,000, 80,000, 100,000, and so on steps of a chain, a Markov chain that's trying to change one assignment at a time. And here I'm showing you one cycle in what's sometimes called simulated annealing. So I'm going to let this run for a while, not worrying about whether I'm making the shapes pretty or ugly. But in redistricting, you couldn't get away with a districting plan that looks like a space-filling curve, right? And so at some point, we're going to have to worry about making the geometry tamer. We're going to have to make the boundaries shorter. We're going to have to make the picture what is called in redistricting more compact, right? And so what you see here is that after those 100,000 steps, we can start to do something Ising-like, where we're going to encourage, we're going to preferentially accept proposed steps that make the boundaries shorter. Does everyone see what's going on there? Okay, but there's a problem. So I've run it hot for a while, and then I've cooled it down to tame the shapes. But what happens after a cycle of this is that I'm back more or less where I started, right? And the reason is, essentially, you can think about this as a process where you're able to extend tentacles, but you can't make a change in the middle of a tentacle, so you end up having to retract it in order to make the boundaries shorter. Okay, so once again, this kind of strategy of like heating and cooling isn't getting around the obstructions posed by this setup. Okay, so here's a new idea for redistricting, is instead of taking a local step Markov chain to make a global step, make a big step. Okay, so here's what we're gonna do. We're gonna take a plan like this one. We're gonna fuse 2 districts at a time, in this case, the pink and the purple. Then we're gonna draw a random spanning tree, and you see one there in the image, of the double district. That's fast, as you all probably know. You can draw a uniformly random spanning tree with Wilson's algorithm in polynomial time. You can draw a greedy minimal weight spanning tree with Kruskal's algorithm even faster. So this is not a slow step. Then we're gonna find a balance edge. That means an edge whose deletion cuts the tree into 2 pieces of about equal weight, or in this case, exactly equal weight. So this is fast if it exists, but not every tree has such an edge. Does that make sense? Is that clear, everybody? Okay. And if it does exist, then I'll cut there, and I will have split into 2 new districts. So let's see that run. So I take a tree, find a balance edge, and cut. And you see this is having a much easier time than the previous chain at like blasting through the initial configuration and giving us something meaningfully different. Any questions about that? Okay, so with Daryl DeFord, L. Knight, and Justin Solomon, we worked on this and wrote some initial survey papers, but we didn't know how often such a balance edge exists. And there's a cool new paper I wanted to highlight from just last year of Cannon, Pegden, and Tucker-Foltz, where they actually showed that the fraction of splittable trees in a grid-like graph is polynomial. Okay, so that proves what seems to be empirically true, which is that this strategy can give you good samples in polynomial time. Okay, so in other words, here is that flip chain from before, and here's our new recombination chain that you get by this spanning tree procedure. And so you see it succeeded not only in obliterating those initial boundaries, but also in making alternative plans that are fairly like plump and compact looking pieces. Okay. Great, okay, so what have we done? We've built a randomized sampling method for exploring the space of partitions, and we've got some evidence, although there's still more to say, that it does a pretty efficient job in giving us random samples. But what kind of random samples? We'll talk more about that, but first let me tell you how we'll use it. So what is all this for? Okay, well here's a real precinct dual graph in Pennsylvania. It's about 9,000 precincts, and they're colored by how people voted for Hillary Clinton versus Donald Trump in 2016. So if you gaze at Pennsylvania, you will immediately see the cities, large and small, by their blueness in this graph. And then on the bottom, what I'm doing is I'm running this recombination Markov chain that fuses districts and splits them in an alternative way at every step. Okay, what's this for? Well, here's a game we can play. Here are a bunch of districting plans in Pennsylvania that were actually drawn by people. And I first got involved in the kind of real world of redistricting when in 2018 I was brought in by the governor of Pennsylvania to kind of help think about what was happening in the court case, League of Women Voters versus Pennsylvania in 2018, that was challenging the districts that had been drawn. So Pennsylvania at the time was one of the few states with split control. One party controlled the legislature, another party controlled the governorship, and therefore had a veto. And so there was a need for some collaboration, right? And so the idea was to try to build a math model to understand what was going on with these districts. Okay, so what can we do armed with a sampler? Well, we can do something like this. We can say, I'm gonna take some statistic, in this case it's a mean median gap, which is advertised as giving some kind of skew between the 2 parties. And I can take all these, 8 plans, and I can mark them by their score on this metric. Now what is usually said about this metric is that 0 would be unskewed or would look fair. And the way that it's normalized here, a positive score would favor Republicans and a negative score would favor Democrats. So the value of the sampling method is that I can create an ensemble or a collection of lots of different plans made according to the rules of the algorithm. And that's what gives me the bell curve type histogram in the background. Okay, so how does this help us understand what's going on? Well, we can take these plans and we can see, if you look at the list, 538 Dem, GOP, and Compact are plans drawn by the Atlas of Redistricting project at 538, the data journalism website, as their best attempt by hand to make a Democratic gerrymander, a Republican gerrymander, and something with the nicest shapes they could. Does that make sense? Okay, and if you notice, the GOP one is all the way over in the positive direction, the Dem one is all the way over in the negative direction, and the Compact one is somewhere in between. Okay, so far so good. So what's the value add of the bell curve? It tells us, it gives us a kind of null model for redistricting without trying to get partisan advantage or have any particular partisan goal. In particular, the algorithm doesn't know anything about votes, right? It wasn't given data with any vote information or any directive to pay attention to that in some way. And so what that tells us, if you take a look at the way the bell curve is shaped, is not centered at 0. So if your guess was that neutral plans would score a 0 on this metric, you'd be wrong. And what this is doing for you is it's quantifying the impact of the political geography, those red and blue dots that we looked at on the graph before, and it's saying where those Democratic and Republican votes are located in the state actually has a net effect of several points in favor of Republicans on this metric. Does that make sense, everybody? Okay, and so if you take a close look, you'll see the governor's plan, which is in a purple color here, sort of sits right at the middle of this bell curve, right next to something called 8th grade, drawn by an actual 8th grade class, which I know because their teacher sent it to me once I was announced as an expert for the governor's office. Okay, so what does this say? It doesn't tell us that the governor's plan and the 8th graders are like awesome. It tells us that they behave as though they were made without any partisan data, right? Which they were. Okay, so that's how this method can kind of help you understand something about the construction principles by giving you a baseline or a benchmark of a world in which certain things are demonstrably not taken into account and others are in particular ways. Okay, any questions? The court ended up adopting what's called the remedial plan in orange, which is sort of on the 0 side of the mountain. So this is how recombination and other kinds of sampling algorithms for redistricting can actually have an impact in practice. However, what I want to emphasize for today's purposes is also that it gives back to us as a mathematical data science community. Okay, so as I said a few slides ago, we've now got this algorithm and it kind of gets where it's going pretty fast, but where is it going? So you can ask, what's the stationary distribution of that Markov chain that we designed? And in this case, it approximately samples from something called the spanning tree distribution. That is, your probability of picking a particular partition is going to be in proportion to the number of spanning trees on its districts. Okay, so the stationary probability of some partition is on the nose proportional to, in this thing I'm defining called the spanning tree distribution, the product over its districts of their number of spanning trees. Is that notation okay? All right. Well, this should sound familiar from many other kinds of partition problems. So first thing I'll say is regular old recombination, the kind that I've been showing you on the last few slides, approximately targets this distribution. And the reason is that your likelihood of if you think about the process of picking spanning trees and cutting them in half, your probability of selecting a particular district is a lot higher if it has more spanning trees. And that's why it roughly targets this distribution. But if you want to exactly target this distribution, there are ways to do that. So in a paper of mine with co-authors, and also a paper that comes out of Jonathan Mattingly's group at Duke, 2 different strategies for getting kind of a reversible Markov chain that exactly targets this distribution. So we know how to get there exactly now. Okay, so why does this give back? What might it be good for? I hope this algorithm might be of interest to plenty of people in this room, because I know from having gone to a bunch of talks here this week already that many of you think about problems like community detection and clustering in networks. And that's what this is doing. It's giving you a fast sample of well-clustered kind of small worldy configurations in networks under balanced constraints in this case. So you're able to say something about the sizes because I need balanced districts for this application. But you could also relax that and let the sizes be what they will. Okay, so what are we doing here? this is a way of finding some geometric structure in a point set that I think would have applications for many of the things folks here like to study. Okay, so that's my redistricting story. And now I'm going to launch into some other short vignettes from the study of elections and what's called computational social choice theory. And I'm going to think about the ways that it synergizes with various things that folks here like to do. Okay, so what is social choice? Social choice is the science of aggregation, right? And we like to think about how to take preferences and put them together, and hopefully we like to do that in a way that's fair. So the story begins, at least the 20th century story begins, with some bad news. Circa 1950, we get Arrow's impossibility theorem, which probably is well known to a lot of folks here, I hope, because it's such a cool result. Arrow tells us that there is only one mechanism possible to aggregate many rankings into one societal ranking while satisfying some very simple criteria. So there's a unanimity criterion. If I ask you all to rank your preferences, and everybody prefers some X to Y, then in the output social ranking, we should also prefer X to Y because it was unanimous among the people who voted. That makes perfect sense, right? By the way, that's the flavor of this subject, is kind of this slightly bullying flavor. You agree with that, right? And then you find yourself stuck. That's what Arrow's going to do. He's going to make us agree with some very simple sounding axioms, and then he's going to tell us we can't have our dreams. Okay? All right, so unanimity is one very natural axiom, and another is independence. If we want to know whether our group ranking puts X over Y, that should be independent of irrelevant alternatives, namely, it should only matter what each of you think about X versus Y. It shouldn't matter where you put Z. Does that make sense, right? I see some nodding, so your Arrow's got you suckered in, right? He says, oh, you like those things? You like unanimity, you like independence? Then there's only one mechanism, and it's called dictatorship, okay? And what that means in this context is dictatorship of the kth voter. So you take some particular voter, Tyler over there, he's the dictator. Welcome to your new fiefdom. And you copy Tyler's ranking and call it our output, our social output. Well, that seems pretty unsatisfying, right? And that's why this is characterized as an impossibility theorem for democracy, right? If you want even a couple of nice properties, you just have to give over control to our benevolent leader. Okay. So this, to my knowledge, is the first in this kind of huge cottage industry of impossibility results. And there are similar results for many other styles, not only other styles of choosing winners, like if we were to all rank our preferences and try to elect just one president, say, but also for apportionment or allocation of resources. There are impossibility theorems for clustering, impossibility theorems for classification, things we all like to think about, and even for redistricting, okay? So everything, this is why we can't have nice things, everything's impossible. All right. Okay, and so we have to respond to this state of affairs in some kind of way. And one thing that we can do, of course, is outsource our vote. But another thing we can do is try to rethink our axioms and come up with kind of relaxed axioms or a relaxed notion of what it means to satisfy them. Okay, so let's think about that. Let me tell you about some new directions in ComSoc, or computational social choice, and then I'll try to connect it back. Okay, so one insight in computational social choice is that randomization is your friend. That a lot of these paradoxes get smoothed out if we allow for randomized rules. And this should be familiar to many of us. Often randomized algorithms can do what deterministic algorithms struggle to do well. And so just for one cheap example, dictatorship is probably off the table if we want to think of ourselves as democracy. But random dictatorship, now that has some nice properties. Okay, so pause and think about that for a second. You probably didn't like it when only one person had the power, but what if you all cast votes and then I uniformly picked one of you to be the dictator after the fact, right? Then if someone had a lot of support, that increases their probability of being elected, right? Because more people could be chosen that would lead to that outcome, okay? And there are lots of different measurable properties under which random dictatorship is far nicer and is worth considering. It's not practical for electing a president, but it has some really nice properties that lead us to think about elections in some different ways. The study of computational social choice has also led to novel voting rules that are really quite intuitively appealing and also have really nice properties. And I wanted to tell you about just one, which is by Kizilkaya and Kempe, I hope I'm pronouncing their names right, called plurality veto. Here's how it goes. Once again, I ask you all to vote. And then what I do is I gather up your first place preferences, and I give those candidates chips, one for every time they were voted first by someone. Okay, so the chips are only for first place votes. So far, so good? Then what I do is I order you all in some linear order. Whether that order is chosen ex ante or whether it's randomized after the fact doesn't really matter for describing the rest of the rule. So there are deterministic and random versions of this. And then what I do is I query you one at a time, and I ask, of the people left standing, of the people who still have chips, which one do you like least? Okay, so that's why it's called plurality veto, because then one by one, voters take chips away from whoever they like least among the ones that are still left. Does that make sense? Okay, so this is pretty nice. Well, before we get to proportionality, this is pretty nice because if you all cast a vote, then after I've ordered you, if I take those chips away one at a time, there were n voters, and there are going to be n times that a chip is removed. At the end, no chips will be left, and that means there must be someone left standing, so there's a winner. And that's how plurality veto selects a winner. Make sense? Okay, and again, without taking a big detour into like metrics of fairness, this has really nice properties. But it was just invented in the last few years by these guys for the study of computational social choice, and we should keep it in mind for decision procedures. Okay, so what else is happening in CompSoc? New axioms, as I said before. If you can't have, independence and unanimity, what are some things that really matter? So it's forced people to sit down and think what kinds of outcomes make us feel that an election was fair. And one prime example is what's called proportionality. If a certain share of the people have a preference, we would like that to be reflected in a representative body in a kind of proportional manner. If you, like me, go around the country talking to people about fairness in elections, this is like #1 with a bullet in people's intuition of what makes an election outcome seem fair. Okay, and so new axioms are trying to capture that in some ways. And also, I have this kind of current pitch that I'm really thinking about, which is so many of those arrow axioms were just yes-no properties. Does your mechanism always satisfy unanimity? Does it always satisfy independence? And that means one corner case can kind of disqualify your algorithm from consideration. And so something that I've been thinking about is once you turn all this probabilistic, can you think about tendencies rather than just always satisfying a property? Okay, so what does that allow you to do? Many things. One thing this whole theory of social choice is good for, one interesting potential application, is social choice for AI alignment. So here's a recent paper just on the archive this year from Vince Konitzer and a large team of collaborators, where they're thinking about how questions of, in particular, suppose you have a large language model, and it gives some responses, and you want to engage in an alignment process where you improve it based on feedback. So you might ask for user feedback. For instance, DALL-E will ask me, did you like that image I made, right? And give me the option to say something. But then the designers have to think about how to use all that feedback. And check out this paper for a really interesting discussion that basically says, hey, come to us, the social choice people, because we know all about ideas for how you can and how you can't harmonize disparate feedback, right, under various kinds of priorities for the outcome. Okay, so I think this is a really interesting application for all of this kind of theory of social choice. Okay, that's all I'll say about that for now. Next vignette, let's talk about ranking. Okay, so New York has an embattled mayor at the moment, you might have noticed. And let me tell you a little bit about the story of how he was elected. So this is the Democratic primary, which is where all the action is in most cities' mayoral contests. This is the Democratic primary for mayor of New York in 2021. So the top 4 candidates were these: Adams, Garcia, Wiley, and Andrew Yang, remember him? And in round 1, here's how many first place votes they had, those 4 normalized to add up to 100%. Okay? Then a bunch of rounds of elimination of less popular candidates are conducted, and in those first 5 rounds, write-ins and a bunch of named candidates are eliminated, and their support is transferred. The proportions for the top 4 barely change after all of those votes are transferred from those first few rounds. Okay, now let's take a closer look at what happens after round 6. So Andrew Yang is going to be eliminated because he has the least support at this point. So what we do is we go to the voters' preferences, and we look at all the ballots where Yang is in first place, and Yang's now going to be eliminated, and so the support is going to transfer to whoever was next on the ballot. This is called instant runoff voting, and it's a form of ranked choice voting that's become really popular around the country. Okay, so Yang is eliminated, his votes split, and he sends a lot of support to Garcia, and not so much to Wiley. And so an interesting thing happens, even though Wiley was ahead of Garcia in rounds 1 through 6, Garcia sneaks past Wiley here in round 7, causing Wiley to be eliminated. And even though her support breaks 2-1 for Garcia, it's not quite enough, and Adams is elected. Okay, so one thing I don't think people followed is just how close that final outcome was. If a few more people, like a lot of Wiley's supporters didn't have either of Garcia or Adams listed at all. So those ballots were exhausted. They could play no role anymore. And if just a few more of those voters had listed either one of these candidates, it's quite likely that Garcia would have won the election. Okay, so this is how this popular system of ranked choice voting works in a nutshell. And now let me tell you a few things about it. So it's become a really pressing problem for those of us who think about studying systems of voting to try to understand how people's ranking behavior actually looks. We'd like to characterize how people rank their preferences. But we have some problems. One is there's a shortage of data giving political ranking preferences. So actually, there was a really beautiful survey paper in ComSoc from last year, I think it was, that did a huge literature review of all the experimental work in computational social choice papers and found that the very #1 data set that's used in these papers is sushi, namely 5,000 Japanese people ranking their favorite sushi. Okay, and here, thank you, Dali, for giving me the sushi debate. All right, that's the image I asked for there. It's super creepy. If you have time later, I'll be sharing these slides. The zombie faces in the audience are pretty amazing. Okay. All right, so what's my point? My point is, whatever you can learn about people's preferences from their dinner selections, it's probably not quite the same thing that drives behavior in ranking political candidates, right? And so one thing that I think is really called for is we have to better understand the landscape of preferences that are out there. And so one thing that I've been working on is building, with my lab, software packages and incorporating repos of data. And so in particular, this is an invitation to play with this data, by the way. So in particular, over 1,000 Scottish ranked choice local government elections, all in a clean and parallel format, are available to you to play with so that you don't have to watch, mackerel take out salmon, if you want to understand how people rank. Okay, that's great. That's some data, but not everything about Scottish local government elections is going to be applicable to, Portland, Oregon, right? And so another powerful tool in the toolkit will be to come up with generative models. And in this case, what I want to generate is rankings. I want to come up with some sort of mechanisms that give me realistic rankings as though suitable for use in politics. Okay, so if you look again in that ComSoc literature for generative models of ranking, you'll find 3 things most often. One is called IC, one's called IAC, so independent culture, independent anonymous culture, and then there are spatial models. So IC is all permutations equally likely. Realistic? Not really. That's not actually what real elections tend to look like. We can talk more about that later. IAC is all profiles of fixed size equally likely. So here's a picture of a simplex on 3 vertices with a lattice of points meant to represent all the ways that 8 voters can rank the candidates. Okay, and this is 8 voters and 3 ballot types. Okay. And then another thing you can do, a spatial model, is where you drop points according to some random process and imagine that some of those points are voters and some of those points are candidates, and that voters rank candidates by proximity, by who they're closest to. So those are called spatial models. Does that make sense? Okay? So all three of these are kind of mathematically tractable, but they're not, in my view, terribly realistic. So something else that we can do that I think actually I'm starting to see in lots of papers in this area is use statistical ranking methods, either alone or in mixtures to reflect polarization. So just a very quick kind of hint of what that might look like. Suppose there are 3 candidates and a group of people has the relative preferences of 20%, 70%, and 10% for 3 candidates. Well, then one reasonable thing to do, which I call the impulsive voter model, is to do what statisticians call placket-loose, and just say, I'm going to draw from the candidates in proportion to their probability that's listed there. I'll draw without replacement. So I'm likely to pick B first, and then I might pick C next. The chance is 1 out of 3 that I would put C next, and that puts A last, and that's how an impulsive voter votes. Okay, so if you followed that, that assigns the probability weight to each of the permutations. Okay, so that's one way that I can model voter choice. Another thing I can do, which is a Bradley-Terry model, but which I've nicknamed a deliberative voter, it's similar, but I consider the candidates pairwise, and I might make a swap based on their relative kind of lengths in the interval that's listed there. Okay, so again, placket-loose just fills in the positions one at a time, probabilistically. Bradley-Terry is proportional to pairwise probabilities of ranking one over the other. And there's lots of other things I can do. Another model that I like to play with is the Cambridge voter. So Cambridge, Massachusetts has been using ranked choice voting continuously since 1941, giving us a big collection of historical data where people ranked up to 20 candidates. And so another thing you can do is label the candidates, pile them together, and draw from historical ballots once you've got candidate labels. Okay, so just to give you a sense that there are various kinds of reasonable ways that you can generate models of ranking. And what does this do for us? Well, remember earlier I said one of our moves for resisting despair in a post-Arrow world is to think about tendencies and not just yes-no global satisfaction of properties. So this is just a teaser image to get you interested, but what I'm showing you here is a model of what the STV, which is a multi-member ranked choice system that's about to be used for the first time in Portland, Oregon. Right? They just changed their system of election, and they'll be using STV next month for their election. This is showing a model for if I have 6 seats, how the representation for a particular group compares to the combined support for its candidates. You can ask me more details about this later if you want, but here I'm just trying to give you a schematic that says I can compare support to representation. And so proportionality, that intuition that we all seem to share about what fair outcomes would look like, would say that representation should be in proportion to support. So you should sort of live on this diagonal. And what we're seeing here is that STV, under these kinds of modeling assumptions and conditions, does a pretty good job of giving fairly proportional representation. The boxes here are proportionality rounded up and down to the integer. Questions? Okay. Great. So this now, once we have generative models, we can ask about and they're probabilistic, we can ask about the tendencies of systems and not just about their most extreme corner cases. Okay, so the last thing I'll say in this vignette is that we need a lot more work in this direction. So a lot of folks that are here like to think about very related problems. For instance, learning ratings. So I know a lot of people here think about, for instance, matrix completion, the so-called Netflix problem, where some viewers have given you some ratings of some movies and you'd like to fill out all the rest, right? You'd like to learn all the missing data. And there are good ways of doing this, and they come with kind of low-dimensional embeddings that let us visualize and understand our data. And I guess my pitch here is that some similar math, but some new ideas are needed, could really help us think about how we vote. So I'm not aware of, and I think I've asked kind of the right people, but please come talk to me if you think there's work in this direction that I should know. I'm not aware of a body of work similarly learning partial rankings from either a history of single selections, ratings, or rankings. So I don't think anything works off the shelf for kind of figuring out how people vote, but it's really close to a lot of things that are very well studied. Okay? And just to say, that's a really impactful applied modeling problem. I mean, I, as much as you, would like Netflix to recommend me good movies, but I'd like my democracy to work even more. Okay. All right, I have a last vignette, and I just have 2 minutes, so let me tell you about it very quickly. And that has to do with weighted voting. So what's the weight of a vote? In the 1960s, the Supreme Court said, 1 person, 1 vote. Actually, they said 1 man, 1 vote, but we're modernizing for them. Okay. So 1 person, 1 vote was supposed to mean that everybody should cast a vote of equal weight. But for them, it was really hard to say exactly what they meant by that, except the district should have about the same number of people in them. Okay? That was the legacy of the 1 person, 1 vote jurisprudence. But notice that this is in tension with other principles that you might consider really good for redistricting, like using whole counties or whole towns or whole communities. For instance, here's a map of Ontario County, New York. It's a relatively small county in New York. And New York is one of 7 states, or so, in which the whole state is partitioned by its towns, right? And so a county in particular, the things that are in the picture outlined in color are the towns in that county. And in New York, the counties wanted to keep voting by town. They wanted, in other words, the board of supervisors for the county should have 1 representative for each town. But that's in tension with 1 person, 1 vote because the towns don't all have the same population. What to do? So a reasonable thing to do is weight the votes of the people. And you might first think you're going to do that by the number of people that you represent. It turns out that's not a great thing to do. So a political scientist named Tom Banzhaf noticed that this could lead to shutouts. So in this example where the towns have these sizes, if you do the math of the 2 to the 5th as 32 different combinations of yes-no votes, you'll see that small town is shut out. It is never pivotal. It's never the case that it votes yes on something, but without its vote, it would have been no. Does that make sense, everybody? Okay, and that means in Banzhaf's way of thinking about fairness, they had no voice if their vote was never needed, right, to pass a measure. And so what Banzhaf said instead is that the probability that you cast that pivotal vote should be in proportion to the number of people you represent. Not the weight of your vote, but the probability that it's pivotal. Does that make sense, everyone? Okay, so how much do you count? This gives us a way of thinking about it. And this kind of belongs to an area called collective or sometimes collaborative game theory. And you might have heard of ideas like Shapley-Shubik values, which are also used to measure kind of your contribution to an outcome. This has other kinds of applications. In finance, people use these Shapley values to think about how business partners might split profits because it gives a way of quantifying your contribution, right? And so this idea of quantifying your contribution has lots of applications. And now to bring it back to machine learning, both of these, plus lots of relatively new ideas, like something from the last few years called integrated gradients, are now used in machine learning for feature attribution or feature importance. So here's a picture from Deanna's talk yesterday, where she said, take a pig, add noise, now it's an airliner, right? And this makes you wonder what it is about image classifiers that's leading to the label that's produced. And so here's an image stolen from Google. You might want to know what it is about this picture of a cat that was cat-like. In other words, which pixels contributed to the label of a cat. And if you stop and think about it for a second, it's really quite exactly the same math that we want to use to think about the power of a vote. We're trying to take all the different little features that went into making a decision and kind of attribute importance and power to each. Okay, so I'll stop there. I'll just say the application in this case, Ontario County actually asked my lab to come up with new weights for its supervisors. And we did this recently. They used to pay $8,000 every census cycle and wait a month to get the weights. Markov chains can beat that in seconds, and we made a web app for them so they don't have to pay anyone to do it anymore. And it has some interesting features, but we have to rethink. So first, we can do the heuristic optimization pretty well. That's great. But as people really thinking about the fundamental mathematics of data science, I think our obligation goes further than that. We want to think about whether the power formulation is capturing what matters, and we want to think about whether the objective function is the right one. And so I hope this will be another kind of chapter in the story of how thinking about voting and thinking about mathematics of data science are kind of mutually contributing, borrowing and taking back ideas and directions. Okay. And I'll stop there, and I'll say thank you, and remember, vote as you please, but please vote.
So thank you for that amazing talk, and for those who have questions, there are microphones in both aisles.
I think I went kind of right to the end, so why don't we take maybe 2 or 3 questions, and then we'll call it a day.
Hello, thank you for your
Hi.
great talk. During your problem about assigning districts, comes to mind one intrinsic problem about having districts, like everybody in the district has a single vote. So something that fits the proportionality and fits the one person, one vote quite straightforwardly is to just have a proportional vote across the whole state. And also that also would enable for would make third parties more likely. So why is that not being discussed?
Yeah, so there are various, so I think the question is, why use these kinds of systems that require so much care and design, and why not just use a proportional mechanism? I think that's the question, right? So, so unfortunately, the problem is these arrow-style theorems tell us nothing works to cure all the problems and pathologies of voting. Like, it's on the nose impossible to cure them all the time. However, it's true that most of the world uses systems that are advertised as proportional representation. And in most of the world, the way that that works is something like a party list. So to fill a legislative body, people will not vote for individuals, but will vote for a party. And then the party gets to fill a number of seats in proportion to their support. And that party maintains a list, and the level of support dictates how deep in the list they get to go. Okay, so actually, something like half the countries of the world use a form of party list. I think party list has some nice features, but it has one huge drawback, which is the reliance on parties, right? And so you get these organizations that mediate public will through a list. And to give you one little indication of the inadequacy of party list on its own, consider this. It's also the case that more than half the countries in the world have a kind of gentleman's agreement where the parties agree in a non-binding way to represent diversity on their lists. So they have soft quotas, sometimes hard quotas, for things like members of minority groups or for women, without which party lists would give incredibly unrepresentative representation on every axis but party. Do you see what I mean? Right? When we think about proportionality, party is only one dimension, and there are actually many others, and no system can secure multidimensional proportionality by design. So one of the reasons I'm interested in things like STV, which I showed you a plot of, is that it's one of the better systems at getting kind of emergent proportionality. Just the fact that the votes transfer and coalesce means that a sizable group with cohesive preferences is going to tend to get pretty good representation. So yeah, sometimes people call these semi-proportional systems. Thanks for the question.
I had a question about your final vignette and this idea of power and the role of small towns in making decisions. I'm sure you get this a lot about the federal government and the legislative branch, the Senate versus the House of Representatives, and some of the frustration of land voting versus people, right? Because the representatives are roughly meant to be proportional to state population, but then in contrast to the Senate.
Yeah, so as you may know, at the time of the founding, there's this like Constitution, and the folks who wrote the Federalist Papers, so especially Hamilton and Madison, but also others like John Jay, are going around trying to drum up support for the Constitution. And so they have to get all these people with different interests to agree. And so the House versus Senate thing was a straight up compromise to get small states and large states to agree. So as you guessed, right, the Senate, the fact that there are 2 senators from every state regardless of its population, that's like a giveaway to small states. Right? And the fact that the House is going to be proportional to population, that's supposed to serve the interests of the large states. These days, it's a very distorting system, absolutely. But it's a legacy of this kind of decision-making of this very practical variety, this kind of horse trading variety. People talk about reforms to Congress in the US, and one of the biggest and most realistic ones is to just expand the size of the House. That alone would help enormously, both with making the House more representative itself in various ways, but also the Electoral College. Each state's number of electoral votes is the sum of its number of representatives and its number of senators. So the malapportionment in the Electoral College would also get better if we enlarge the size of the House. So that's one of the most realistically achievable ways to mitigate that kind of distorting problem. Okay. Any last question? Okay, great.
Very nice talk. My question is more about how to collect data, how to collect votes. What is your opinion about using blockchain technology?
Yeah. So I had the good fortune about 5 years ago to be on a study committee at the National Academies of Science about election security and election technology. And we talked about many things over the course of those 2 years on that committee. One is the kind of impossibility of internet voting. I've become convinced it's very difficult. Another thing I learned is the whole vendor landscape of voting machines and why it's so complicated to get better voting machines. Come talk to me, that's something I know a lot more about. And the third is blockchain won't save us. So I could drill down and talk to you more about those opinions, but also I could point you to the study that was released by this working group, which is called the Future of Voting Working Group. That kind of details why some of these promising sounding ideas are non-starters. Okay, thank you very much, and it's been a pleasure.